Here we're going to take a look at some word problems and see how slope and intercepts come into play so that we can form an equation and then use it to solve some different scenarios. So the common case here is that we're going to use slope-intercept form, so our y equals mx plus b. Let's start with describing what b would represent in the context of a real-world problem. So b is our y-intercept, and it's what happens when x is 0. So really it's when our input value, or x typically, is 0. And with that, in cases of real-world problems, we're typically in our first quadrant, so where everything's positive. And what that could represent is, from reading left to right, is a starting point. So what we often describe this as is an initial value. So like it might be some cost at the beginning, or it might be some, like, if we have a financial account, it's like how much money we deposited at the beginning and then it grows from there. Different cases like that. So it's some initial value or starting value is going to be our y-intercept. Then m, so our slope, that's our rate of change. And sometimes that's described to us in words, which could be, typically the word you want to look for is per, like miles per hour, dollars per second. That kind of terminology will relate to our slope. And typically it goes, our like output units or our y units per x units. It's typically how it goes. So with that, we can kind of recognize rate of change. So let's see some different cases here and how we can relate it to our y equals mx plus b form. So to start producing a new model of custom wheels, a company will have to purchase $30,000 in new equipment. Each wheel made costs them $40 in supplies and labor. Write a formula for the total cost T of producing Q wheels. What will be their total cost in the first year if they expect to sell 240 wheels? Okay, so what we have here is we have this big cost right at the beginning. We had to buy some new equipment, so we have this big cost of $30,000. Then from there, the cost kind of increases for each wheel made. Per each wheel, we have $40 in supplies and labor. So what we're starting to get here is this initial cost, which is that $30,000. And then we could call this a variable cost because it's changing. It'll change based on the number of wheels that we make. And so we have this variable cost of $40 per wheel. And that terminology right there is our slope and intercept. That $30,000 is going to be our y-intercept, and that variable cost is going to be $40 per wheel. So what we could do is form an equation, T equals, and our slope is going to be that $40 per wheel plus that $30,000 from that initial cost. So we could see here, and what can help is just plugging in values. So if we made one wheel, we would have that $30,000 plus $40. If we made two wheels, we would be adding $80 in. 3 wheels, $120. 10 wheels, add on $400. So we have this variable cost part, and then this fixed cost, or this initial cost of $30,000. So then their question is, what will be their total cost in the first year if they expect to sell 240 wheels? So what we could do is then calculate T equals 40 times 240 plus 30,000. And with that, let's go ahead and just plug that into the calculator with 40 times 240 plus 30,000 for 39,600. And that's a cost, so that'll be in money. So $39,600 would be our total cost for 240 wheels. Okay, so that was a case where they just told us what the slope and intercept is. This next one, the balance in your college payment account, C, is a function of the number of quarters, Q, you attend given by the equation, C equals 20,000 minus 4,000 Q. Interpret the slope and C-intercept for this equation. So with this one, we're just interpreting. So looking at this, I see that negative 4,000, that's our slope, and that 20,000 is our y-intercept. So starting with the y-intercept, so that's our initial value, and in this case, we're given C, which is our account. That's like where our account starts out. We're starting out with $20,000. So let's actually go ahead and put that in terms of the C-intercept. Interpreting that, we would say the college payment account starts at $20,000. Or we could say we begin our college payment account with $20,000 deposited or something like that, or with a balance of $20,000. Then from there, so our slope is, and we need that negative, so it's negative 4,000. And like I was saying up above here, it's like our y units per x units. So in this case, our y units would be dollars, and our x units, which is our input, is the number of quarters. So what I could see from this before I make a sentence is that we're decreasing because of that negative, and we're decreasing by $4,000 per quarter. So to interpret the slope, we would say we pay $4,000 per quarter. Or we could say the balance decreases. In fact, well, no, that's good too. But we could say balance decreases by $4,000 per quarter as well. That works. So a few different ways to word it, but those all get the message across of we're beginning at 20,000, and then from there our account is decreasing as we pay for each quarter of college. All right, that's a good interpretation one. Let's take a look at this next case. So, working as an insurance salesperson, Maria earns a base salary and a commission on each new policy. So Maria's weekly income, I, depends on the number of new policies she sells during the week. So she's going to have some base salary that she's paid no matter what, so that's fixed. And then what's going to change is this commission based on the number of new policies that she sells. So we have our variable part and our fixed part. Last week, she sold 3 new policies and earned $760 for the week. So we have here is it's a coordinate, really. This idea of with 3 policies came $760. And the week before, she sold 5 new policies and earned $920. This is a second coordinate where we have 5 policies with $920. So it's like we have data that we're collecting. What we can use is just 2 coordinates to find this equation. So we're going to calculate her income in terms of n, but what we need is slope and intercept. And then what we're going to do is interpret it. But to get slope, what we'll do is our standard difference in y values over difference in x values. And I'm going to go ahead and plug that into the calculator. So I'm going to set up my fraction, 920 minus 760. over 5 minus 3 is 2. So we have a slope of 80. So I know I have I equals 80 times n plus b, but I don't know what b is yet, but what we can do is plug in one of our coordinates. Doesn't matter which one. I'll go ahead with the 3 and 760. So that tells me 760 is equal to 80 times 3 plus b. So 760 is equal to 240 plus b. Subtract 240 from both sides for 520. And with that, we get our equation I equals 80 times n plus 520, which tells me her base salary, so Maria's base salary is that $520 each week. And she earns $80 per policy. So we have our starting pay at $520, and then from there it increases with $80 per new policy that she sells. Okay, let's keep going. I know lots of word problems, but it's nice to see all the different scenarios together. Okay, we have scientists are conducting an experiment with a gas in a sealed container. We have the mass of the gas is measured, and the scientists realize that the gas is leaking over time in a linear way. So we're losing things. So each minute they lose 8.8 grams. So that right there is telling me about slope. We are losing 8.8 grams per minute. 7 minutes since the experiment started, the remaining gas had a mass of 334.4 grams. Something that tells me is I could make a coordinate with time and mass where 7 minutes has passed and we have 334.4 grams. Okay, just making little notes to myself. All right, let x be the number of minutes. So instead of t, let's use x. And y be the mass in grams. Use a linear equation to model the weight of gas over time. So what we have is we have the slope. So we know we have negative 8.8. But what we don't know is our y-intercept, but we have a coordinate to plug in. So we can solve for b. So we're going to plug in 7 and the 334.4 to solve for b. So we will take 334.4, add on 8.8 times 7 for 396. So our equation is y equals negative 8.8 times x plus 396. How much gas would be left after 31 minutes? So that would be plugging in 31 for x. And solving. So negative 8.8 times 31 plus 396 is 123.2. And to get our units, that's how much gas we have, so that would be in grams. If the linear model continues to be accurate, how much time must pass for all of the gas in the container to be gone? So this would be a case where the amount of gas would be equal to 0. So we're solving 0 equals negative 8.8 times x plus 396, which if we add the 8.8x to both sides, just to make that nice and positive, what we'll get is x is equal to 396 divided by 8.8. Which is 45. So that would be 45 minutes. We would end up with an empty container with all of the gas having leaked out. Our next example here deals with distance equals rate times time, which we sometimes call the DIRT formula. So D equals R times T. And really there are so many iterations of this because you can solve for rate, you could solve for time, but it comes from this relationship right here. So this is going to come up throughout the term because it's just comes up a lot in our word problems. So we have here is it takes Andrew 30 minutes to drive to work in the morning. He drives using the same route, so we have the same distance, but it takes him 10 minutes longer, and he averages 10 miles per hour less on the way home. So we have these two directions, and what I find really helpful is to make a little chart. So let's see, driving to work, driving to home. And what we're going to look at is how distance, rate, and time come to play with each of those scenarios. All right, so distance is going to be the same. He's going the same route. In terms of rate, whatever rate he's going to work, we take 10 miles per hour away as he's going home. So that rate decreases. So if he's going 50 miles per hour in the morning, he's going 40 miles per hour on the way home. Then in terms of time, we have 30 minutes. And actually, I'm going to put this a little bit to the side, 30 minutes. And then it takes him 10 minutes longer to go home. So that would be 40 minutes. Now, why I'm putting that to the side is because we have two types of units. We have minutes, and then our rate is in terms of hours, since those were miles per hour. So we want to make sure we work with these in the same way, either both in minutes or both in hours. I'm going to leave the rate as miles per hour. Instead, what I'm going to do is convert these minutes to hours. So what we could do is think of it as a fraction. So like 30 minutes out of 60 minutes, 40 minutes out of 60 minutes. So that would be a 1/2. And this would be a 2/3. All right, so with that, we end up with two equations. We have distance is equal to rate times time of 1/2. We also have distance equals a rate of r minus 10 times 2/3. And those distances should be the same, so what we could do is set these two equations equal to each other. So 1/2 r is equal to, and then I'm going to multiply that 2/3. I'm going to go ahead and distribute in. So that would be 2/3 r minus 20/3. All right. From there, I have all these fractions, so I'm going to go ahead and multiply everything by the least common denominator of 6. Which would leave me with 3r equals 2 times 2r, so 4r, minus 2 times 20, 40. Subtract r from both sides, subtract 4r from both sides, multiply both sides by -1, so r is 40. So it is taking us 40, or we're rather going 40 miles per hour to work, which means we're going 30 miles per hour home. And with this, we can find the distance using either of the equations, but let's go ahead and use, 40 is r, and we're going to multiply that by 1/2, which is 20. So that's going to be a distance of 20 miles. And you could find that with this case as well. If you plug in 40, it would be 40 minus 10 is 30. Times that would be 10 times 2, which is 20. So we'd get the same thing out in the end. But there's our distance, rate, time. Just be careful of those units and making sure that they line up. Okay, the last scenario I want to look at is with mixture. So with percentages, with mixture, this can also come up with like bank account scenarios where you have a percent interest, or if we're adding a percentage on, it usually comes from multiplication. So let's see what we have here. We have how many gallons of a 4% alcohol solution must be mixed with 8 gallons of a 39% alcohol solution to make an 18% solution. Okay, so we're combining two things and ending up with a result. So it's like we have one solution. Let's call this solution A, solution B, and we have our end result. Now, whenever we have these percentages, say I want to know how much alcohol is in there. So like 8 gallons of a 39% solution. So the amount of alcohol is 39% of 8, which when we work with percentages, we need to use the decimal form. So like that would be 0.39 of 8. So that would tell me how much alcohol is coming from solution B. And then from this first one, I don't know how many gallons I have, so that's going to be my variable, but 4% of that is alcohol. So we're going to take 4%, which would be 0.04 of however many gallons we're taking there. And what we're ending up with is 18% alcohol solution. So we're taking 18% of, and then we have an idea of how much we'll end up with. We have these 8 gallons, and then we have this unknown amount of gallons. So what we'll have is that unknown amount plus 8 gallons. So each of these, the format goes concentration times amount, concentration times amount, concentration times amount. And then from there, we can go ahead and start solving. So 0.04x plus, and I'm just going to get a side calculator going here. So 0.39 times 8 is 3.12 equals, I'm going to distribute that 0.18 in, plus 8 times 0.18 for 1.44. Let's go ahead and get everything with x on one side. So I'm going to subtract 0.04x from both sides. I'll also subtract that 1.44 from both sides. So let's see, 3.12 minus 1.44 is a 1.68. Equals 0.18 minus 0.04, so 0.14x. Divide both sides by 0.14. So 1.68 divided by 0.14 is 12. So how many gallons of that 4% solution would we need? We need 12 gallons. And what we'd end up with is 20 total gallons of an 18% solution. Okay, lots of examples in there, but all cases of solving linear equations with various applications given certain information.